Good afternoon, CS109. How are you guys doing today? Fantastic. You guys know this, but it's our penultimate class. We have class today. We have a fun little lecture on Wednesday, and then that's it for lectures in CS109. I can't believe we're at that part. It feels like just yesterday we were starting and we're like, hey, let's talk about probabilities. And we were doing counting. Oh, what good times. We have a very fun celebratory lecture today. We're at that part of the quarter where these aren't things that will be on the exam, but it's also a really fun chance for me to just talk about what I think is interesting and part of the future of probability. And I have a novel lecture for you guys, one I've not given before, and one that I'm really excited to give. So I was thinking about what should we talk about? And there's all these fun things to talk about. I was like, oh, I could talk about like Kale divergence, or I could talk about bounds. And then something happened last Thursday that's really worth talking about. As you might have heard, there was a new release of this large language model called GPT. Just quickly, has anyone ever heard of this? Okay, it seems like something worth talking about. Interestingly, it coincides, this last week was the world's biggest AI conference. In fact, we had a couple papers there. I decided to stay because I wanted to hang out with you guys. I got sick a couple times this quarter and I just wanted to chill with my CS109 fam. But that's why you're seeing so much happening in the world of AI. And I thought long and hard about it. I just thought it'd be so neat for you guys to learn some of the probability behind some of the biggest movers and shakers of today. So in today's class, we're going to learn about how DALL-E works, how GPT-3 works, and if we have time, I can tell you a little bit about some of my most recent probability work, if you guys find that interesting. You want to do it? So it's also going to be on the board, so I practiced and everything. We're going to try and do this on the board. We're going to get rid of the screen in a second, but not quite yet. Because before we jump into thinking about the wonderful ideas behind these algorithms that maybe are going to have a rather profound impact, let's just play a little bit. So if you haven't seen GPT, it's a pretty simple API. You can write text and it will produce text. So for example, here I wrote, write a thought-provoking poem that explains the difference between maximum likelihood parameter estimation and MAP parameter estimation, but it should be sung by a pirate as a sea shanty. So it says, I, ye landlubbers, listen to me as I sing of parameter estimation, of maximum likelihood and MAP, you see, two approaches, both with their own reputation. Maximum likelihood, it seeks to maximize the probability of the data that's seen. MAP adds a prior to regularize and balance this trade-off between bias and precision. I feel like I got it to be more piratey other times, but you can be like, okay, be more piratey. How do you even spell piratey? Is that it? Oh man, I, ye scurvy dogs, lend an ear to the tale I spin a friend. And this is, behind the scenes, a machine learning model a little bit like we've learned. So that's one of the things we're going to talk about today, like what's going on with this model and what are the great ideas behind it? What's the difference between what we've learned in CS109 and the technology behind GPT? But we're also going to talk about a different model that might seem pretty separate, but there is similar ideas that go on behind the scenes. And this one doesn't produce text, but instead it produces images. So I said a photo of a beautiful coast live oak. These aren't real photos, they don't exist, they were just generated. And you guys have probably seen this before, I'm just trying to catch everyone up. And before we go to the board, there's just one more picture that I want you guys to see before we go in there, because I'm going to at some point refer to Gaussian noise, and you need to have a visualization to go with it. So this is a picture with no noise. And this is a picture with some Gaussian noise. And when I say some Gaussian noise, notice how it looks or a little bit distorted. Every single pixel has its original value, but we've added some Gaussian sample into the pixels. In this case, it's on both the red, or all the red, green, and blue channels. This is with a little bit of Gaussian noise, and this is with a ton of Gaussian noise. You can't even see the dog anymore. Okay, questions, comments, thoughts before we jump into this? Okay. Okay, let's make that screen go up. Let's get lights all on, as bright as we can get it in this NVIDIA auditorium. Okay, so this is our roadmap. We're gonna start with thinking about that second algorithm, the one that can produce trees. And it's a really interesting story. Did you know it actually took place at Stanford? Like the great idea behind how you can create images from neural networks was a simple idea that happened here not too long ago by a fellow called Joshua Sol-Dickstein. Okay, so where should we start? Maybe we could start by building a little bit of a roadmap, and I want to put it here in the center. I want to talk about the 3 models we should have in our minds. One model is what you're doing for homework. The second model is going to be this DALL-E, and the third model is going to be GPT. And on some level, they have a lot in common. They all have a big neural network. Well, maybe yours has a logistic regression, but we're going to think of them all as black boxes. So if we start with your algorithm, so this is like your P set 6. You built a little machine learning algorithm. And the machine learning algorithm takes features which come as a list, and it produces a prediction y, which is an element of 0, 1, which is a really fancy way of saying you built an algorithm that could take some inputs and it predicts out either a 0, 1 binary prediction. But we also want to add in DALL-E here. And DALL-E does something different. It's also a neural network, but we're going to be making DALL-E tree style. And what DALL-E tree does is it doesn't take any inputs, but every single time you run this neural network, it's going to produce not a 0 or 1, but it's going to produce an image. And our version is always going to be an image of a tree. So let's get out our blue marker, and let's draw ourselves a little bit of a tree. Woohoo! What do you guys think? Not quite DALL-E, but it's an all right drawing, right? And then the final neural network we're going to think about is going to be GPT. And GPT takes in some text like let's say you wrote I love, and you throw it into the model, and it produces more text. So let's say CS109 and pancakes. Okay, so that's our goal. Let's see if we can understand these 3. Now, hopefully you're understanding your own problem set 6. So maybe we could start by jumping into thinking about how this DALL-E model works. Can I start with just asking you to come up with it? Because there is a history here. In this task of running a neural network and having it produce an image, there's been a long history of cool creative ideas. One creative idea that's no longer used is you'd have 2 different neural networks. One neural network would create images, and the other neural network would try and decide, was this image produced by a computer, or was it produced, or is it an actual image from the internet? And these 2 competing neural networks would train against each other, and eventually one of them would get really, really good at producing images that would trick the other one. That was a great idea, but as I said, Stanford not too long ago, someone had another great idea that changed the game. It's a great idea that you're going to understand deeply by the end of today's class. But I want to just give you guys an idea to play. Come up with your wild ideas. Just make up a way. Like if I said you had to create a neural network that's going to generate a picture of a tree, how would you do it? And some of the questions you can ask yourself are, what data would I use? And then what would I do with the data? Imagine somebody gives you a big neural network. How could you set the parameters to that neural network with some data? Have a moment, just be playful, make up ideas, say something silly, be like, I'll send my neural network to a pirate who knows so much about maximum likelihood estimation that they'll figure out all the parameters. Have a good time, think about it for a second before we jump into what is the great idea behind DALL-E. Okay, talk to the person next to you. And I'll take a moment and practice my tree drawing. expectations, but there's a small chance that we'll just like totally revolutionize the world because like this is such an open field. Okay, let's hear them. Good ideas, bad ideas, funny ideas. We'll take them all. Okay, what's your thoughts?
So for DALL-E, what I would do is I was like for trees, I'd scrape Google, find like a bunch of images of trees, and then have DALL-E like create a bunch of images and then see which one most closely matches the data set of trees.
Okay, scrape Google, produce an image, and then the loss can be something like distance to closest tree. Great. Fantastic. Okay, yes, an idea.
Try and make a network to identify trees and then, in some sense, run it in reverse.
Ooh, okay. So we're going to have like a tree network, kind of like ours over here. You put in a picture and either says tree or not, but we're going to then run it in reverse. And we're going to say, okay, you're a tree, mess with my pixels. Whoa, I like it. Reverse a classification image. Or predictor, sorry. Okay. Yes, one more idea.
So maybe you produce like 3 images, one of the red pixels, green pixels, and blue pixels, and so you kind of have multiple variable outputs, and then for each of those outputs you have 256 like values that it could be, and so you take all the pictures in that you've scraped from Google and then evaluate what's the probability that in a picture of a tree this particular pixel has this particular level.
Oh, okay. So you said a lot of good things. Like one is when we're making this picture, we're going to have to not just output a 0 or 1, but we're going to have to output the pixel values. That's going to mean the red, green, and blue pixel values. So that's going to be our task. And then you said, you know, we could set it up so that we say like the most likely pixel, or like the pixel that's most likely given what we've seen. Okay, okay, great. So we're going to have to predict pixel values. Awesome. And we want maybe the most likely given tree. Okay, these are all very, very good ideas. Shall we go into, because it's the beauty of what goes behind DALL-E is that it's when you see it, you'll be like, oh, okay, let's get behind the probability, but I can appreciate that that works. Now, one of the things that's complicated about the world is you've got all these images, but on Google, say, not all of them have labels. You can get lots and lots and lots of pictures. Some of them might have labels that say what they are, but some of them won't. And there was this interesting idea. You could take any image, picture of a tree, and here's something you could do to it. We'll explain why you may want to do that, but here's something you can do. At the moment, it's a little bit unmotivated. Take your picture. And one of the things you could do is you could break your picture. And one of the ways you could break your picture is you could add in some noise. And let's say you chose Gaussian noise. Yeah, that's kind of a pretty reasonable thing to do. So I'm going to add in 20% noise. And by 20% noise, maybe like, 1 in 5 pixels, I could add in some Gaussian noise. So to give you an idea of what that looks like, if we zoomed into some pixel, pretend for a moment that pixel, all our pictures are black and white. This is the black and white. Black and white. Or like the artsy version. Imagine every pixel is black and white. That makes it a little bit easier. We don't have to think about red, green, and blue. It's just that if you zoomed into any pixel of a tree, if you looked at a pixel, it would just have a number. And let's say those numbers are between 0 and 1. So let's say this is like a 0.5. When we add in Gaussian noise, here's what I mean. For some of these pixels, we're going to add in a random sample from a Gaussian. And we could choose any Gaussian, but let's say we chose a pretty reasonable Gaussian that has like a mean of 0 and some sort of variance, right? And so maybe when you sampled from this Gaussian, you got like a 0.1. So then the resulting pixel value is 0.6. So when I say add in Gaussian noise, it's something that you guys could do right now. Like you could pull up a computer, and if I give you a pixel value, you could do, hey, SciPy, sample from a Gaussian with a particular mean and a particular variance, and then add that to my old pixel value. And you could do this. You could then take this image, and you know what you could do? You'd be like, not noisy enough. I'm going to add a little bit more noise. So you can say, like, I want something with 40%. And then eventually, you could keep going until you've just got the world's noisiest image. So, you know, we could add 20% noise, and we could add another 20% noise. And now it's just starting to look pretty noisy. And eventually, when you get to 100% noise, everything just looks like a random value from our Gaussian. And you just can't see any tree anymore. I haven't described any neural network. There's not a neural network here. It's just a way that you could take all these gigantic tons of images from the internet and you could start to manipulate them. But there's this growing mystery, which is, why would anyone want to do that to your poor images? Like, you're making them harder to see? Like, why is that a useful thing? Do you guys want to try and think about it? Like, I've left this like tantalizing clue. Just reflect on it. What could you do with this? Because I say, like, when I say this is like $1 million question, I feel like the person who figured this out is now one of the lead researchers at Google. So probably was worth like $1 million for the person who did figure it out. Yeah, probably. Jesus, what a time. Well, you could do this to a lot of images. And why would that be nice? Okay, an idea.
I think it's very similar to what Vijay said, because you're starting with the outcome. So you know the outcome that you added the features that separate it. So you're constantly, so it's conditioned on the outcome. So constantly adding noise, you condition it to what you do. Such a way that it keeps learning how the outcome should look at various scenarios, so that when you reverse it, it can still work.
Yes, you're on to something that is really, really in the right direction. So yes, we're going in the right direction. It has this relationship between the outcome, the cleaner image, and a noisier image. Yeah?
Maybe you could de-blur the blurry images to create different trees.
Yeah, that's it. This is the first great idea. So the first great idea that kind of changed everything about image generation is we could build a little neural network, and its job is pretty simple. It doesn't have to do any complicated predictions. So we're going to call this idea number one. And idea number one is we're going to build a neural network. It will take in an image. And that image is going to be of a tree. And it's going to have some noise in it. Let's try and recreate that image as well as we can. And we're going to build a little neural network. And this little neural network, when it's done, it will produce a picture that has removed 20% of the noise. So could you make this data set? Could you make your training and test set? Yeah, you can make yourself a big one. Take all of Google, take all the images you've got, add in noise, and then you can feed it into your neural network and say, here's the noisy version. Can you predict an image? And then I'll see how good a job you're at removing the Gaussian noise. But that doesn't generate a whole tree, that just removes some noise. So how could you generate a tree like this? Well, you start here. Generate random samples from a Gaussian for every pixel. Then run that completely noisy version through your neural network. You'll end up with something with 80% noise. Take the result, put it through your neural network again. You'll end up with something 60% noise. Put it through your neural network again. You have 40% noise, and you keep going, and eventually it's got a tree. What if you wanted a different tree? You're like, that's not pretty enough. I want a new one. You just start with different random noise. If you create different random noise, you put in like this completely noisy image through your neural network, and it'll try and remove noise in a way that'll make it look more like a tree. And you repeat this 5 times, and you'll have a picture of a tree. Okay, questions? Yes?
In this example, does the black box, is that strictly just removing 20% noise on each step, or do we have 5 boxes, one from going to 100 to 80, one from going from 80 to 60, one from kind of incrementally like that?
Just one box. Now, one of the things that I'm going to try and give you guys the great ideas. There are some small details that are helpful. I think this black box also takes in which step you're on as one of its X's, one of its features. But that, as I said, that's not the great idea. And if you got rid of that, it would probably be just fine. Yeah, just one box. And they call that box DALL-E. Yes?
Is it removing like just random 20% noise, or is it more sophisticated than that? Like, how does the training part work? Like, how's it getting feedback?
So we'll talk about it in mathematical detail. I promise, because you guys actually, you're totally ready to understand all the mathematical sophistication of precisely what it's doing. But let me give you the big picture first. It has both of these images. How? Because it generated them, right? And so it puts in one, and actually, realistically, you end up with your predicted one, and then there's the true image of the tree. And maybe the true image of the tree is slightly different, because when your neural network tried to make a tree, it didn't get it perfect. Oh, all the colors. You guys, this is such an enjoyable marker experience. So maybe, when you made your prediction, you got it slightly wrong. And when I say slightly wrong, what do I mean? Well, we know what the truth is, right? We had the clean image, and then we added the noise ourselves. So we have the input, and we have the truth, and then we can see your prediction. We can be like, how good is that prediction? Now you ask, as I promised, not only do I want to explain this to you, I just want to give you the level of sophistication that you are ready for in CS109. We'll talk about that detail, but let's get that big picture first. Also, I want to explain myself pedagogically. I wanted to draw on the board for lots of reasons, and one of the goals is to slow myself down, and so that we can keep it all up on the board so you can see the big picture as it unfolds. Plus, it's kind of fun for me. Yeah, question?
If we wanted to do like the full DALL-E, so not just making trees, but making whatever, would we like train it to de-blur images in general, and then instead of using completely random noise, like blur a tree or something else?
So it's actually pretty simple. I'm going to remove that detail so we can just focus on the great idea. But the simple idea is you also insert text. So you say, this is an oak tree. Whatever the prompt the user gave you, and that text can help it guide its de-noising. Now, when we understand GPT, we'll have a better sense of how you could do that. And until we talk about GPT, let's just assume that all it does is make some trees. But it's actually a pretty small addition to make it also be guided. Okay, question?
Could you explain a little bit more of the intuition behind like the benefits and drawbacks of running it like 5 times versus just like a neural network would say like 5 times as many layers?
Oh, that's such a good one. Well, the question is, why do it 5 times instead of just going all the way? So I actually used to take, and I used to live in San Francisco together, and our labs were right next to each other. At Stanford, you're like, hey, Chris, why didn't you invent, diffusion? And I'm like, that's not important right now. And I guess I was hanging out with him. We would get on the Caltrain. We were writing a paper together around the same time. So he was telling me a little bit about it. And honestly, it didn't work. He just tried to do it all at once, and it wasn't successful. But if you did it step by step, it seemed to be a little bit easier. And there is a little bit of an art form to some of this stuff. And I don't think there's a deep theoretical reason why putting it through 5 times is better than making 5 times bigger model. I will say this, though. At the time when he was a researcher, he had access to a pretty big computer. But we're going to talk about this in a second. One of the other things that's happened is scale. DALL-E is trained on massive supercomputers, which maybe that means that in the new version of DALL-E, they could go straight. It might have just been the constraint of his computer. Good question. Why do 20%? Yes?
This is kind of Random, but is DALL-E like open source? Does it continue to train every time people use it and get better?
Not open source, and it does get better as people use it. So, I mean, this is such an interesting ethical issue. So these models are expensive. They cost about $500 million to train. And there's only a few companies in the world who have access to them. And I think they're trying to figure out what this means monetarily as part of it. But you know what they said? They said, this stuff's too powerful, we can't just give it away. And they're not completely wrong. You know, like on some level, there's probably some version of GPT that maybe shouldn't be out there in the wild. People could use it in really nefarious ways. But that's what they said. But it's hard to ignore that the value of these things, even though they cost $1 billion to train, they might be worth trillions of dollars to whoever can figure out the smartest one. So that's such a good question. Okay. Yeah. Question.
So are we starting with like a blurred image of another tree, or just a blurred image that can become anything?
Good question. When you start with just a blurred image. So if I gave you a fully trained DALL-E, here's what you would do. You would create the size of the tree you want, and for every single pixel, you just sample from a Gaussian. Its value would be sampled from a Gaussian. Now, if we want to get a little more detail, there'd be a red, green, and blue, but just assuming it's black and white, every single pixel would just be sampled from a Gaussian. So you look at it at the beginning, and it just looks like static on your TV. But then you put it through our model once, and it starts to look a little bit less like static. The tree it looks like will be defined by whatever random noise you started with. Like that seed is where oh, that's so beautiful. It's the seeds where the tree sprouts from. You see what I did there? Not important. And then you run it 5 times, and then you have your fully grown tree, and you're like, oh, we went through so much together. Okay. Yes?
Is there like one reference picture that the system is trying to make it look like, or is it just...
So this is one of like the trillion images they've found on the internet. One of the secrets behind all of this is that the internet has a lot of data. So they'll do this once for this tree, and then they'll do it for the next tree, and then the next tree, and the next tree, and we'll get every tree we get. In fact, there's so many trees on the internet, it often won't look at the same tree twice. Like once it's done it, you can just put it away. Now there are different training schemes. I don't have that many tree pictures. I would probably use trees multiple times. Okay. So, yes?
What's the advantage of using random noise as opposed to just white pixels?
Good question. If you started with white pixels, you would always get the same tree every time you ran it. And I suppose if you, the idea here of like trying to figure out where the noise is, I think one of the, well, you know what, that's a cool idea. I'm just going with that's a cool idea. So one of the things we could have done is you could have taken your tree and you could have just like whited out every single, like 20% of the pixels and then white out 20% more. And then your job is to fill in the 20%. That sounds really good. But certainly you have this problem that you'll always produce the same tree.
Why would you always?
Well, one of the reasons you get different trees is because the noise is different each time. Like every time you create your image, it starts with different noise, like when you're in the generation phase. But if you always start with the exact same seed, it'll, you know, when it removes its 20%, there's nothing about this that is stochastic in nature. The stochasticity, the fact that you get different trees starts with the fact that you created a different seed. But I like that, and you know, we should try that out. An idea.
Is the denoising model, is it just ran on the entire image, or does it only like denoise like 20% of the pixels each time?
Well, it's run on the entire image, and it tries to denoise 20%. But we're just at the start of things. You know, people are trying to use this in different ways. You can imagine this is a foundation upon which you guys could build some cool ideas. And one of the cool ideas is, you know, maybe we want to just fill in specific pixels. You know, maybe we just want to remove this branch. Or there's lots of neat things that you could do on top of this technology. Okay, one more question, then I'm actually going to tell you there's an even better idea than this.
Is the variance of the Gaussian noise chosen to ensure that the training propagates through the network?
There's a lot of art form. I'd say that's not a closed discussion. So people choose variance in lots of different ways. Diffusion actually comes from a physics idea. Like this idea of removing Gaussian noise has existed a long time in the world of physics, and they've been very thoughtful about how they choose variances. For today's example, we're just going to use constant variance. But if you read the original diffusion model 1, you can see that they're changing noise in intentional ways throughout the training process. Though again, it would have worked just fine if they hadn't. Okay, now this turned out to still be a hard problem. What have we talked about so far? We've talked about the architecture. We've talked about how you can get data. So at this moment, if I give you a fully trained DALL-E, you could use it. You could put in noise and you could get progressively better images. What I haven't told you is if I gave you an untrained DALL-E, how you could do the training yourself. And one of the reasons is that it's a little bit hard to think about the likelihood. Like, what's the maximum likelihood of an image given another image? I don't know. Some people could have figured things out. There's like cool ideas like an elbow lower bound loss. That was fine. But somebody realized, hey, there's a slightly easier problem. And it's very easy to think about the probability in really first principle ways if we solve this easier problem. Did you guys know there's an even easier problem? Want to hear about it? Okay, here's how it goes. Same starting point. The starting point is still going to be, you have a picture of a tree with some noise and you want to denoise it. Got to keep the noise consistently red. I like this Christmas theme going on. And this time, the output is not going to be a tree. You're like, what? It's not going to be a tree? I thought we were making trees here. No, pal. We're no longer in the tree making business. We're now in the noise prediction business. So this time, we're not going to predict trees at all. Instead, we're going to say, if you gave me this tree, instead of predicting the tree without noise, I'll predict the noise. What would you guys do with that? If I said, here was my input, I predict that this is the noise, could you turn that into a tree? I see some nodding. Just like Diffusion. Okay, an idea. Somebody's got this. Somebody's thinking it. Yeah, in the back.
Oh, like taking the input and subtracting the noise?
Exactly. If I gave you an image and you predicted where the noise was, and this noise could be positive or negative, and let's say you predicted positive and negative values, you could just subtract. You could take this image, subtract out, and then you should be left with the unnoised image. So it turns out that these two problems, somebody realized were the same, and this problem was A, much easier, and B, much easier to think about probabilistically, because we still have this task of how could we train this puppy? So you could have predicted your noise, and then I know exactly where I put the noise. Let's say you've forgotten that one. And now we have to think about what's the likelihood of the true image given what we predicted. So a lot like maximum likelihood estimation. Now, what I'm going to tell you is going to extend to the whole image, but can we just jump into one pixel for a hot second? If we just jumped into one pixel, let's see if we can get that up there. If we jumped into one pixel, you could imagine that if you looked at, say, this pixel over here, you could have two numbers. We're going to have like, y hat, and I'm going to be a little clear that y hat is a result of the neural network. So I'm going to say that it was a function of the parameters, just like the output of a neural network was a function of its parameters. And let's say y hat was 0. Let's say the true one was 0.6. Let's say y hat is 0.5. And the true y, the true amount, or actually we're predicting the noise, sorry. The true noise is 0.1. And let's say you predicted a 0.2. So at this pixel, you made a prediction of the amount of noise. You predicted it was a 0.2, but in truth, it was a 0.1. People said, you know what? Let's think about this as a random variable. We can think about y as being a Gaussian, because we know it is a Gaussian. And we're going to assume that the Gaussian takes on the mean that was your prediction. So we can say its mean is equal to the prediction you had, y hat of theta. And then we're going to say it has some fixed variance for now. We can call that k. And then we can ask a likelihood question. We can do it for one pixel, but of course we could think about every pixel as being independent because our Gaussian noise was independent. But let's think about one pixel at a time. We can talk about what's the likelihood. We'd say, what's the likelihood with respect to our parameters? And as you guys know now, it should just be the probability density function of our random variable. Probability density function of a normal. That's something we've seen before. You know, do you guys remember this from back in the day? Oh man, I'm already nostalgic. We're gonna have to say goodbye. Don't be strangers. You guys should come say hi whenever you see me. That's not important right now. It's not goodbye yet. We got a lot of GPT to talk about before that. But you remember this little expression? Oh man, it just like makes me sad to think that this is one of the last times we'll be talking about normals. Okay, but anyways, you have the value of y you observed. So we observed at 0.1. We know the true mean was 0.2. And remember, this is y, and this is y hat, or sorry, this is y hat, and this is y for those people following along. And you have 2 sigma squared. So we can say, how likely does the result of our neural network look, you know, or how likely is our random variable assignment? But of course, you know, we don't really think about likelihood. We like to think about log likelihood because it's easier to work with. And if we took the log of this, you know, you'd end up with a log of this expression. You know what this thing is going to look like? A big old constant. Because, like, don't forget, it's only this thing here that's got parameters. The parameters went into generating this number, but the parameters didn't go into anything else. So when we think about, you know, this as a function of parameters, everything that doesn't have a parameter looks like a constant. So this whole thing is going to be log. I'm going to draw a smiley face for my constant. You're like, is that a Greek symbol? No, it's a smiley face, but it's a smiley face. Why? Because I'm so happy when I have to deal with constants. What's the log of this? It's going to be a constant. Plus, you know, log of multiplication is going to be log of this plus log of this. Log of e raised to the power of something. Remember, exp just means e as a base raised to the power of. Cancels out. What a good time. Am I missing a negative? No, yeah. Is there a negative here in the Gaussian probability density function?
There's a negative.
There's a negative, yes. What a crazy time to be alive. I forgot. But then I remembered, just in time. Okay, so this is going to become negative. And I could write 0.1, or I could write y minus y hat. And remember, y hat was something that came from our parameters. Squared divided by a smiley face. You're like, you can't divide by a smiley face. Oh, yes, I can, because it's just constant. Now, this is all looking well and good, but there's just one other thing I want to point this out. We want to choose our thetas to be the argmax of this function. And the argmax of this function doesn't care about this constant. And the argmax of the function doesn't care about this constant either. So the argmax of this is just going to be the same as the argmax of y minus y hat squared that was for one pixel. And because every pixel is independent, the likelihood should have had a big product here. And the log likelihood should have had a big sum here. And this thing would just have a sum over here. And if I throw that sum back in, I'm feeling a little bit fancy, so it's going to be pink. You get an expression that you might have heard people talk about. It's the sum of squared errors. These are all your predictions, and these are the true values. You look at the difference between those two and square it. And you sum that over all of your pixels. And you're going to try and choose the parameters that maximize this. Now, it's a maximum of a negative, so it's the minimize of the sum of squared errors. And so you're going to try and choose the parameters that minimize the sum of squared errors. It's a beautiful piece of probability that leads to a very, very simple algorithm. So going back here, what you're going to do, you put in your noisy image. It goes to the neural network, you make your predictions. Now you have the predictions and the truth. You calculate the sum of squared errors, and that tells you how good a job you did. but that doesn't tell you how to change the parameters in the neural network. How are we going to change those parameters in the neural network?
Gradient descent.
Gradient descent. You can't set that derivative equal to 0 and then solve for them because there's going to be a big old set of parameters in here. But what you then do is you just say, hey, there's a lot of parameters in here. For every single parameter, I can ask the question, what's the derivative of this objective function with respect to every single parameter? Oh man, it's time to talk about history. I'm going to try and throw in some interesting histories because I can't believe I'm so old I lived through some history. Man, my field is moving fast. So if this is time, and this is like AI progress, I would say it has kind of felt to me like this. And there was this huge moment here. And this was, I'd say, about 2013-ish. In 2013, some amazing programmer came up with this amazing piece of technology. It has a name. It was called autograd. Before that date, when I made neural networks, you know what I would do? I would construct my neural network, imagine all of the neurons, all the logistic regressions connected to each other. And then me and my buddy would go to a cafe and we'd spend our day doing all the derivatives. And if it was a complicated neural network, we'd start with the last layer, then we get the derivative of the next layer, and we get the derivative of the next layer. We made weird neural networks, weirder ones than I ever see now. We'd have like trees and stuff, and it was great. It was a good time. But we'd spend the entire day doing derivatives. And then there was this great idea that started in a program called Torch, which was originally written in a language called Lua. Does anyone program in Lua? One person a little bit. Yeah, I used to program in this thing called Lua. It's like a Brazilian programming language, and it was the first one that had autograd. It was such a big deal. We all learned this Brazilian programming language named after the moon. Anyway, and so what did autograd do? Autograd meant that in Python, I would say, here's my neural network. It has this layer, this layer, this layer. Here is my objective function. And then I would say, automatically do all the calculus. And it would just be one line. And the neural network would know how to do the chain rule. It would know how to do the chain rule, like the derivative of this with respect to the end layer, the derivative of that with respect to the previous layer, and it did all the chain rule. So no one has to do derivatives now. It's important to know that they exist, and that's the magic behind the scenes. But autograd, you guys live in the future. What a time to be alive. Okay. What that means is that as an architect, what you really need is just this function. You have to figure out what is the loss function that is probabilistically inspired, so that I can talk about how good a job I'm doing, and then I can ask the computer to update the gradients. Okay. Wait a second. That's kind of it. Insane. Now, in terms of the architecture here, there's a lot of things you could do. But there's one thing that turned out to be really important. It's got to be big. And this is going to be even more true for GPT. But for GPT, there's two things that people realized, not too long after autograd. They're like, since we don't have to do our derivatives, what if we had a bigger neural network? And we just got more data. And people got better and better at building special chips for doing automatic differentiation and doing the actual gradient ascent. And people got bigger and bigger computers. And they noticed two things. Training time. I'm going to draw two graphs. And on the x-axis are two different things. On the x-axis is how big are our models, and on the x-axis over here is how long do they train. And originally, when I built models, I would try and make more and more parameters, but my models would kind of look like this. And I never got that big. Let's say this is like 10 to the 10th, and this is like 10 to the 10th. And my model would eventually look like that. Like, what does that mean? That means as I'm training, it gets smarter and smarter and smarter, but eventually I hit what we would call a plateau. And then I would call it a day. I'd go have like an adventure with my friends, and I just assumed that's what would happen. And for the longest time, I believed that all neural networks would hit the ceiling. Until one day, somebody was like, you know what? I'm just going to get a lot more parameters. And when you got to a certain level, all of a sudden, people started to escape the plateau. And they started to hit these points where it didn't seem to have a plateau. It wasn't maybe getting that much smarter that quickly. But they hit this point where if you could just take a network like this one, put more and more parameters into it, and give it more and more data, it would just keep getting smarter. And then people did the craziest things. Like, I used to train these things. Like, you guys think about your homework assignment. Like, how long do you train your gradient descent for logistic regression? I don't know, 5 minutes at most? It really does plateau out pretty fast. What, you think people do longer? Yeah, but we tell them how many steps to do, so I don't know. Okay, well, it depends on your computer. Like, maybe you train it for 10 minutes. Well, once people realized this, they started doing something that wasn't the most ecologically sound. They're like, what if we just keep on all the supercomputers and not turn it off for like a year? And like every time the programmers go to sleep, they wake up, it was still training. And people just went and went and went, and it started getting better and better at denoising. So these are the main narratives that led to DALL-E. I hope you guys feel a little bit like this is demystified. This was a great idea. But it's a great idea you could have had, right? Think about the person next to you, think about the person on the other side. If it's not one of them, maybe it would be you who could have come up with this. And there's many more ideas like that out there. This second idea, that was a nice one. Instead of trying to predict removing the noise, just predict where the noise is and we can do the math. And that this leads to a nice little piece of mathematics where if you think of the noise as being Gaussian, when you do the log likelihood and the argmax of it, you end up with this negative sum of squared errors. Now, I'm gonna say autograd, man. I'm like such fans. If I ever meet the people who did autograd, I'm gonna be like total fanboy. I'm like, you guys are amazing. And I wouldn't say this is a great idea. I think it's just like more like, okay, great, we can do that. But that's kind of the big story picture. So I'm going to go get my blue marker, which is my favorite. I'm going to say, that was part 1 of today's adventure. So I'm going to give you guys the pedagogical pause. Now, guess what we're going to do next? I won't tell you. I'll leave it as a mystery. Take your 2 minutes pedagogical pause, and then we'll continue today's lecture. Okay. I got a little liberal in my use of the boards. I have to think of it. So what we've talked about so far is DALL-E. And that was fantastic. And if I had to name that part of lecture, if I had to give it a title, it'd be denoising, because that was really the most beautiful idea in all of this, that we're actually going to be really creative with our data, add noise, then train a neural network that can predict the noise, and since the noise is Gaussian, we've got a really nice likelihood function. We can do MLE. If I had to name the next part of this lecture, I would call it Attention is All You Need, because that was actually the name of one of the papers that led to the great idea that really transformed this. And, you know, the original GPT, there's a lot of history here at Stanford. Like, the original GPT was written by a person called Andrej Karpathy, who was, yet again, also a PhD student in Stanford. So a lot of this stuff was created by people just like yourselves. So language presents a problem. In our previous model, we dealt with generating images, but now we're going to start thinking about language, and there's a bunch of reasons that language is really difficult. One is we ascribe so much meaning and intelligence to language. We take it very seriously as a society, but there's also more practical challenges. And if I could point out one practical challenge about language is that it's variable length. You know, if you think about your features, we always had a fixed length number of features that we gave on our problem set 6. When you think about GPT, you know, we could control the image size. It would always be fixed size images. And that just made a lot about our architecture a lot easier. But one of the things I'm going to point out about language that's quite difficult, besides the fact that it's such a complicated concept, is that it's going to be variable length. So first, let me tell you a little bit about the bad ideas that didn't work. So one of the bad ideas that didn't work so much was to build this, well, when I say it's a bad idea, it will be part of our final solution. They build these little neural networks, and the idea of the little neural network would be you would put your language through the little neural network, and the neural network could produce two things. It could produce both the next word, so maybe you'd hopefully predict socks, and it could also produce a vector. And if you took that vector and you put this vector into the neural network, it would hopefully produce the next word. And you could have different words coming as inputs. And so they built these little neural networks that you could use recurrently. You could put in, you know, CS109 through this network. It would produce maybe rocks, and it would produce a vector. Then you could put rocks to this network, it would produce socks, and it would create another vector. And this vector would then become the output, or sorry, would eventually become input over here. So like what you produce as output then becomes this input. And we could call these things state vectors. So you have like state at time 0, and one of the things that your neural network would make is state at time 1. It seemed like a good idea, and people made language models like this for a long time. And they were fine. They just couldn't do that much. And they weren't that impressive. You asked for a recipe, and it would just start like giving you gobbledygook. On some level, though, this wasn't what the really great idea was. The really great idea here was, hey, let's borrow some of those ideas. So we're still going to have a neural network. It's still going to take in a state vector. And it's still going to produce the next word. But the great idea here is we're going to build a very special neural network that we're going to call an attention neural network. And this attention neural network is going to take in all the words we've seen so far. and it's going to put them together into a really, really, really special format that we're going to call the context vector. So we have this neural network that I have not described to you yet, but what it's going to do is going to take all the words and compress them into some important piece of context. Now, let me give you a little bit more layer of detail about what it's going to output. There's a lot of words in the English language. This little neural network here is not going to just produce a word. That's a little bit oversimplified. Instead, it's going to predict for every word in the English language the probability that that word is next. So I'm not going to try and draw all the words in the English language, but you can imagine it creates a big old dictionary. And it'll say like rocks. You know, that's pretty high probability, it's 0.001. And you could say like Stanford. Maybe that's less, maybe it's 10 to the negative fourth. But for every single word, we're going to produce a probability. If I gave you this neural network, you gave me a set of words as input, it would go through the special layer, make context, and start with some random state, and then it produced these probabilities. How could you go from these probabilities to picking a word? I've said a lot of complexity, so I want to take a moment and solidify. I'm going to give you guys a minute to think about it. Why don't you talk about it with the person next to you? And the question I want you guys to figure out is, if you had a neural network and it produced word probability mappings, how would you choose the next word? Talk about it, but also take it as a moment to figure out what's confusing about this, and we'll take some questions afterwards. Okay, go for it. Think about it. Okay. An idea? What would you guys do if I gave you a neural network, it took a couple words, and it gave you back this dictionary where words with the probability that they come next? What would you do?
Likely word.
You could choose the most likely word. That is not a bad idea. And that would be possible. But here, let me just tell you about one thing that would happen. Do you remember when we had that great idea of we had like the white pixels, but I said, if you did that, then every time you ran this, you would always get the same image? If you choose the most likely word, then every time you write CS109 rocks, you'll always get that most likely word. Because again, there's no randomness in the neural network itself. So while that would be a good idea, you'd always get the same production. We want it to be a little bit different each time. Okay, yes? And
What if you just pick a word that's like likely enough, and then
yeah?
just like sample randomly from all the words? Is it good enough? And then put it in.
There it is. I don't know if that's what you're going to say, but sample randomly is what people do. So you get this whole dictionary, and you know what? They kind of treat it like multinomials. It's like this big dice. It's got all these sides, and here's the probability of each outcome. And they take this gigantic English language side dice, and they roll it. And you imagine they have to have their arms like this because it's so big. And they'll get one word, and it's most likely to be the thing that has the highest probability, but it could be something else. But let's say for now, when you sample, you get the word rocks. But you know, if there was another high probability word, when you roll that dice, it's very possible you get something other than rocks. So at this point, oh, sorry. It doesn't say rocks, that's what it just had. CS109 rocks. Socks. What did you say?
Great.
Yeah. CS9, no, you can't say CS19 rocks is great. It's always rocks, socks. Like, what else can you rock? And roll? No, it's definitely socks. Okay, so socks is the word we choose. Sorry. Now, at this point, we don't want to just produce one word. We want to keep doing this. So in the same way that when we were doing the denoising, we'd reuse our neural network to remove more and more noise. We're going to reuse our neural network. So at this point, we have a neural network. It's produced the word socks, and it's also produced another vector, another set of neurons. You know, you can imagine, you can just take the last layer of activations here and treat that as a vector. And then we're going to reuse that exact same neural network. But now instead of having CS9 rocks, we have CS109 rock socks. And we're going to put that through this special thing we haven't talked about in detail called attention layer. Again, that's going to give us a set of neuron activations. And then we're going to use the same neural network. That neural network wants a state vector, it wanted a context vector, and it's going to output another dictionary. And I don't know what comes after socks. Can somebody help me out here? What could go after socks? Be the large language model. Period. Yes, certainly. That happens with high probability. So when you sample from this dictionary, you get period. And it just keeps doing that. Now, this idea had been around for a while. And people had tried it, and it just didn't work that well because they hadn't figured out the magic that goes into this little mechanism. And what they do with this little mechanism was kind of interesting. They built a neural network that could take in any word. So let's say you had CS109. They built a little neural network, and that little neural network would produce a single value called an intention word. Let's say that this would well, actually, I guess it would produce two things. Let's say this is word 0, because it's the first thing. It would produce a little embedding of the word, and it would come up with an attention value, so a number between 0 and 1. And this little neural network, it also took the state vector. So you would take whatever state vector you had, and it goes into this layer here. So we have state times 0. And any word, you can put it through this second neural network. We'll call this the attention neural network. And the big thing is that it produces this attention vector. This context that comes out of attention is really a simple thing. Let's say the context would be equal to the sum over all the words I of the words vector weighted by its attention. And the really simple idea here is this little neural network is like a focuser. It would say, before we even start to process this sentence, let's have a neural network which says what we should be paying attention to. For example, when you're producing the word socks, you probably only need to work at the word rocks. It doesn't matter what came before. If you put a lot of attention on rocks, you could realize that the next word was socks. But it might be the case that, when you put period, you have to look and realize, what are you saying rocks? And be like, oh, let's put attention on this word. Since this word CS109, obviously it rocks socks, period. And so it can know what to focus on. And it seems like a simple idea. But this simple idea we think was one of the biggest changes in architecture. And then all of a sudden people were like, okay, this stuff seems to work. And then again, when they start to scale up, they ended up with things that could speak and create things that look like meaning. I'm almost done. I know there's a lot going on in these two boards and I should take a lot of questions. But that's kind of the big idea. We're just missing one thing. You could get in Python and you could define in PyTorch, which is the successor of this torch that was originally written in Lua. And you could say, I'm going to define all these neural networks. I'm going to just define my states, and I'll have a neural network that takes this as input. It's kind of like you're making a tree, the graphical structure. You make your graphical structure, and then you call autograd. You'd say, I want you to update all of these based off words. Where do we get these words? The dictionary is kind of good. Yes, there's many words in the dictionary, but in order to do this, we're going to need a whole bunch of not just words. We want to have some like words, we're going to make a prediction, and then we want to know, was our prediction good? Yeah, an idea.
Look at a bunch of written stuff.
Yeah. They get a lot of written stuff. You know where they find all that written stuff? Yeah, not in the library. The internet's got a lot of written stuff. So somewhere on the internet, somebody was writing a passage, and they're like, Bayes was cool, but CS109 rocked socks like fox? Like a fox. And someone wrote this, and then people would take this word on the internet and they would create training examples. They would say, okay, I'm going to put this into my neural network, and I'm going to see, is it able to predict this next word? The last thing we would need if we wanted to bring this thing full circle is not just how you'd use the neural network, but how you would train it, which means you need to have something like this. You need to have the MLE scoring function that we're trying to optimize. So this says CS109 rocks. We look at the real word and it's a socks. And you know what? We had produced a probability. We'd said how likely it was. And so since we had a probability of socks, we could use the multinomial probability mass function to say, okay, I thought socks had this probability. I could say, what is my loss function given that? So very similar to how you did your loss function here. Here you use the Bernoulli loss function because you had a class with 2 labels. Here you've got a class with multiple labels. And here you'd use your probability of 1 in your Bernoulli probability mass function. And here you use the multinomial probability mass function. And then you're done. You've got a likelihood function. And the next big idea was just data. Give it lots and lots and lots of data. Now, to be clear, what I described is probably GPT-3. It's unclear what is behind GPT-4. They say it's going to come out between December and February. They say it's going to be as big a change from GPT-2 to GPT-3. And I can't tell you what's in GPT-4. Maybe they're like, you know what? If instead of attention, we do retention structure, then everything works out. Who knows? Maybe they just came up with a better chip that could do more autograd more quickly. I'm not sure, but that's the future coming. I know this is probably a lot the first time you see it, but maybe you can appreciate that there's a finite number of things to learn. There's a lot more structure here. You can appreciate for a language, it's really nice that you don't have to do your derivatives, that all your derivatives can come for free, because there's this interesting reusing of neural networks that gets really hard to do the math around, but computer can go through and do all the chain rule that you want. At the end of the day, you're producing probabilities, so MLE is still a tool you can use. And this really simple idea of, I'm going to take each input and decide how much I should care about it, that simple idea was kind of the equivalent of denoising. And it seems that attention is really good. In fact, this single idea was so good, you start to see it in all other places. Like in algorithms that try and learn how to drive. Instead of trying to do some sort of really complicated network, now they're trying to use attention, where they can just say, okay, if I can see out my car, what should I be paying attention to when I make my next decision? So this simple attention neural network turns out to be very helpful. Again, autograd's a big deal because now you have 2 different neural networks with parameters all over the place, doing lots of different complicated things, and all you would need to do is string up your neural network and then say, computer, do the optimization for me. Okay, questions, comments, concerns? Yes?
Backtracking a little, but I was wondering, instead of doing gradient ascent or descent,
Like, why can't you just solve for like the closed form of the like gradient along likelihood and then find your parameters that way? Is it because like it's just too hard of a equation?
Yeah, it is too hard of an equation. I'm pretty sure there is no closed form. So let's talk about why it's hard. First of all, if you had one parameter, you would solve, take that gradient, set it equal to 0, and then solve, right? If you had two parameters, you have two equations, two unknowns, and then solve. These things have close to 1 trillion parameters. So you can set up 1 trillion equations, 1 trillion unknowns, and then try and solve. But it gets worse. You know, when we think about our neural networks, they're all logistic regressions. Like at some point you have the activation of one logistic regression cell inside this massive neural network is going to be equal to something like a sigmoid of the weighted sum of the inputs times by the weights. So we're going to say inputs I, weights I. Did you guys notice how the predictions we were making, if this inner part ended up being positive, we would just predict a 1. If this ended up being negative, we'd predict a 0 in your own homework. But we still had the sigmoid. Originally, the sigmoid was helpful because it allowed us to interpret the result as a probability. But it turns out the sigmoid does something else that's really important. If you got rid of that sigmoid, you said every single neuron was just inputs multiplied by weights and you didn't put it through the squashing function, it turns out that you could have 1 trillion parameters, but it would still be equivalent to if you just had a linear system. This sigmoid here makes it non-linear in really complicated ways. It also makes it basically impossible to do closed forms. Oh, I want to tell you guys something. And you guys tell me if I did the wrong thing. How's that? You're like, Chris, what did you do? I know. When I make logistic regression, I use a sigmoid. But sigmoid has this really nasty property that if you look at it, it has all its values are positive. It's always between 0 and 1. That's great if you're thinking about an output, but if you're somewhere in the middle of a neural network, it turns out having all of your weights have positive values is really annoying and problematic for really subtle reasons. And so people don't want their inner neurons to be shifted. So you could do a sigmoid and subtract by 0.5. Did you guys want to know there's another function? Tanh. Anyone seen this before? Tanh? Yeah, the hyperbolic tangent. It's not that special. It doesn't have a probabilistic interpretation. You wouldn't use it for the final layer, but you can use it in internal layers. It looks a lot like the sigmoid, but it's just centered nicely. And it turns out this is a really big deal if you want to have inner layers in a neural network. There's other things you can use rather than a tanh, but no matter what you do, sorry, I went on a tangent, but you need this, you need this non-linear piece, right? You need to like put through some squashing function to make sure your whole thing doesn't end up just being linear. It is important, but it also makes it impossible to do the closed form, set it equal to 0. You're like, here's my question. I'm like, whoa, Tanh, and then we're back. But I need to get this off my chest that even though we use sigmoid for the final layer, in the inner layers we actually use tanh, which looks very similar, but it's centered around 0. Yes?
How does the array of parameters for attention interact with the ones for the next word and the relative probabilities for those words? Is it that you first do one and then the other?
So in the forward pass, you can imagine in the forward pass, you first do the attention on each word. And what you do on each word, every word will end up with its vector and also its weight. So you do this for every word. That's your first thing. Then the second thing is you run this little function. You end up with the context. At this point, you have a vector for context. You always keep a state vector. It's just always, it's like a set of neurons that are just holding on to some memory. Did you want to know what happens here when you have to merge those two things into this box? Okay, wait for it. If you have a neural network and it's getting inputs from the top and it's getting inputs from the side, check out what we do. So it's just a vector, a little bit like your x's, but now you've got two of them. We do this. We stack them. You take your first one, you take your second one, you stick them together, and now you got one vector going into your neural network, very similar to how you have your x's going into your logistic regression. So, we use this is just a diagram, but really these two are both inputs into the neural network. Okay. Is that a question? Yeah.
Exactly what the state 1 and state 2 actually do.
What makes it meaningful?
What is it even storing?
They're just neurons. They're just you have you have some neurons that produce values, and you have a bunch of them, and then you store them in memory. And in theory, it's holding on to memory. It's holding on to ideas that it's constructing as it's going. So maybe it's trying to produce a poem in pirate speak, and it's producing it word by word, and it has to keep track of where it's going in some space, and it stores in these neurons. And I don't even understand what's going on with those neurons, but it's some sort of black magic, and it just keeps it so that it can make its prediction for the next word. It's amazing.
It's kind of earlier we had that converging structure for neurons, but this is just a different way to shape them.
Yeah, and you can imagine. Much like when we were producing images. Remember we were producing images, you could produce one pixel and then another pixel and then a third pixel. It's a lot like that. These are just a bunch of neurons and they're all going to be produced a little bit like their pixels. It's just we're going to store them as state and use in a different way. We're actually, wow. I was 2 algorithms, how long could it take? But I wanted to draw on the board because I wanted to go slow and go to the details. And maybe if I could leave it on this it does, normally I was the person who was kind of hoping we'd never hit general intelligence. I was kind of hoping we'd stay in the simple world where we just do our educational things. But I must say, until Thursday, I was like, oh yeah, people are making their GPTs, how cute. Oh my God, DALL-E, I can make a picture of a tree. This is fantastic. And then I started playing around this a lot over the weekend. And in my heart, I feel like it is a bit of a change. And it's not such a big change. It's not like the whole world's going to reorient around this stuff. But it is a new technology. And you know what it reminds me of? Did I say I was so old I remember when mobile phones became a thing? I was a computer science major, and all of a sudden we have mobile phones. You can make apps. And there was a rush. Everyone wanted to make an app. My God, I probably should have made an app. If I made an app, maybe I could have retired young. Note to self. Hey, you want to go into a business? We're going to do some cool GPT-based neural network. No?
Let's go put in the PSET app.
Oh, we'll put in the PSET app, and then we'll all do it together. And did mobile phones change everything? Yes and no. There was a whole set of new ideas that came. Things were possible. It was a very exciting time to be a young researcher. Because all of a sudden, I got to the cutting edge a lot faster. When I look at GPT-3, I've told you a lot of what I know about GPT-3, and soon you guys can be on that cutting edge. And I think that's a little bit exciting. It's a little bit terrifying because there's uncertainty, and uncertainty is always hard, except for people who study probability. We like to make decisions under uncertainty. I don't know, and I would welcome you guys to this conversation. What do you guys think it means, and where do you want to see it go? How would you like to shape it? What role would you like to play? And then come back on Wednesday. It's our very final class. We're going to have to say goodbye. I'll miss you. Don't be strangers. Have a fantastic day. You guys rock. See you on Wednesday.